Okay, check this out. Suppose we start with a rectangle like this. And let's say I want to connect the diagonal from here to here. Would you agree with me that this right here is just going to be 1/2 of the whole thing in terms of the area? Sure thing, right? Because we can see we have a very nice triangle here. If you fold it, they match, so that would be just 1/2. Now, I'm going to put down the x-axis here, and then the y-axis here, and do a rotation about the y-axis, like this. So what are we going to get though? From the triangle, we will end up with a cone. And then from the rectangle, we will end up with a cylinder. So we will have a cone instead of a cylinder like this. And let me just put the picture down for you guys real quick. Here is the cone. And then we have the cylinder that goes around it, like so. Now, question for you guys. In terms of the volume, how big is the cone compared to the cylinder? Is it still going to be 1/2? No, in fact, not anymore. The truth is, this cone is actually just 1/3 of the cylinder. Well, of course, seeing is believing, so let me show you. All right, check this out. One, two, three. Ta-da! Now I'm going to show you how to use calculus to prove that the volume of a cone is actually just 1/3 of the cylinder with the same base radius and also the same height. Check this out. So right here, this is the radius of the base and this is the height of the cone and also the cylinder. If you come back here, this is the R and this is the H. First, we need an equation for this line. Well, it's just going to be a line, so we need a slope. We go up by H and we move to the right by R. So it's H over R, and then multiply by X. And the y-intercept here is 0, so we don't need to plus anything. Now, what we'll do is, we'll take a horizontal rectangle like this, and then we are going to rotate it about the y-axis. So this rectangle will become a disc, like this. And in fact, a disc is just a very thin cylinder. And the cylinder has the volume pi r squared times the height. But since this right here is supposed to be really thin, we will call it the thickness. And this right here is so thin, it's just a small change in the y. So we label this right here as dy. And the radius of the disk is just the horizontal distance. It's x and changes, so keep it as x. Now, for the blue disk, it has the volume pi times the radius, which is x, square that, and times the disk, times the thickness. So it's dy. Okay, this right here is just one disk though. We want to add up all such disks from the very bottom to the very top. And we'll use the super version of addition, which is the integral. We integrate it. Well, because we are in the y world, take a look right here. The starting y value is 0. And then the ending y value will be h. So we have to go from 0 to h. And this will give you the volume of a cone. Yeah. This right here is of course called the disk method, and this thing right here is called the volume of revolution. Very cool. Now let's just go ahead and work it out. But x is not allowed in the y world. It's okay, because we know that y is equal to h over r times x. Multiply both sides by its reciprocal. So x is equal to r over h times y. So this becomes the integral going from 0 to h, pi and then r over h times y squared dy. And now we can just work this out. First, we have pi r squared over h squared. They are all constants, so you can put that in the front of the integral, like this. And then we have the integral from 0 to h, y squared dy. I'm pretty sure some of you guys can see why we have the 1/3 already. Because right here, we have to add 1 to the power, we get 3, divided by the new power, which is 1/3. So, well, divided by the new power. Yeah. Divided by the new power. And we get 1/3 here. And now we can put the 1/3 to the front. So this is pi r squared over 3h squared. And then we just have y cubed. And we go from 0 to h. Plugging h, we get pi r squared over 3h squared times h cubed. Plugging 0 doesn't matter because it's 0. And then right here, reduce it. Ladies and gentlemen, we have 1/3 times pi r squared and h. And this is precisely the volume of a cylinder. And then the cone is just 1/3 of that. That's it. Now I have a question for you. Imagine that here you have a bucket of ice cream. Well, if you take out the ice cream in a cone way like this, and now I have a question for you. Suppose right here, and now I have a question for you. Suppose, and now I have a question for you. Imagine that right here we have a bucket of ice cream. And let's say if you just take out the amount of ice cream like this in the shape of a cone, you don't get half of the amount of the ice cream. You just get 1/3 of the bucket of the ice cream, right? So the question for you is this. How are we going to do it? So we're going to scoop it up. So do not just say halfway up. That's too boring. Because you have to use a spoon. You have to do it in like a, like curvy manner or something. How are you going to do it so that the amount that you take out is half of the amount of the bucket of the ice cream? So I will phrase it like this. And I'll tell you, you have to do it in a curvy manner like this. And we would like to know what curve this is, so some k, so that this volume is equal to the volume of the cylinder around it. Alright, so this is 1/2 of the cylinder. Yeah, what's the k? Well, think about it and I'll show it to you in the next video. That's it.